For most of us, being on time is, well, it's a good thing. But in the world of computing, sometimes being on time isn't just a good thing, it's the only thing that matters. And we're not talking about your computer booting up a little bit faster. We're talking about situations where a few milliseconds, a tiny fraction of a second, can be the difference between a mission succeeding and $1 billion catastrophe. Okay, let's get into it. So take a look at this. This is the Ariane 5 rocket. Just 37 seconds into its very first flight, it veered off course and, well, exploded in a pretty spectacular fashion. Now, the investigation afterwards found something fascinating. The cause wasn't a bad engine, it wasn't a fuel leak, nope. It was a software error. A piece of code taken from the older Ariane 4 tried to cram a big 64-bit number into a tiny 16-bit space. That caused an overflow, the system panicked, the guidance computer failed, and boom! It all came down to a single timing bug. And believe it or not, this was not a one-off thing. The very first space shuttle launch was scrubbed right there on the launch pad because of an incredibly subtle timing bug. Turns out there was a 1 in 67 chance, just a tiny probability, that a brief system overload could knock the backup computer out of sync with the main one. Now, a 1 in 67 chance might sound low, but when you're dealing with human lives and billions of dollars, you have to plan for the absolute worst case. And that is the world of real-time computing.
Okay, so this brings us to a really important point, something a lot of people get wrong. We hear the term real time, and we immediately think it just means really, really fast. But that's not it at all. See, fast computing, like your gaming PC, is all about averages. How many frames per second can it average over a minute? Real-time computing couldn't care less about the average. It is 100% focused on predictability. It's about meeting every single deadline, every time, with no exceptions. Here's the textbook definition, and it's actually perfect. In a real-time system, a late answer is a wrong answer. That's it. Think about it. If your car's airbag controller figures out exactly how to deploy the airbag, but it delivers that command 1 second too late, well, the calculation was worthless, right? The timing of the result is just as critical as the result itself.
So the big question is, how do you actually pull this off? How do you guarantee this perfect timing? Well, the magic happens inside a little piece of software called the scheduler. You can think of it as the brain of the whole operation, constantly deciding what the CPU should be doing at any given microsecond.
I mean, just think about the computer inside a modern car. It's simultaneously monitoring engine temperature, checking for wheel slip to control the anti-lock brakes, managing fuel injectors, and, running the map on your dashboard. How on earth does one single computer juggle all of that critical stuff at once? The answer is the scheduler. It's like an air traffic controller for the CPU, making sure every single one of those jobs lands safely before its deadline.
All right, to really get how these schedulers work, we kind of need to learn their language. First, you have a task. That's just a single job, like check the temperature sensor. Next is computation time, which is the absolute longest time that task will ever take to run. Then there's the period. That's the rhythm. How often does this task need to happen? Maybe every 10 milliseconds. And finally, the most important word of all, the deadline. That's the drop-dead point in time by which that task must be finished. No excuses. Okay, now that we've got the lingo down, we can look at the actual strategies these schedulers use to make sure every deadline gets met. It really boils down to two main philosophies, two different ways of thinking about which task is the most important at any given moment. Our first strategy is called rate monotonic, or just RM for short. And the rule for RM is, well, it's dead simple, and it never ever changes. The task with the shortest period, the one that has to run most often, always gets the highest priority. That's it. So a task that runs every 10 milliseconds will always get to interrupt a task that only runs every 100 milliseconds. Simple as that. And what this simple rule creates is something called interference. Because that high-priority task A can cut in line anytime it wants, it delays the lower priority tasks like B and C. Now, under rate monotonic, this is all totally predictable, but it means that a task can take way longer to finish than its own computation time would suggest, just because it keeps getting pushed aside by more frequent, more important jobs.
So you might be wondering, how can you be sure this will all work, that you won't miss a deadline? Well, there's this magic number, about 69.3%. If the total amount of work all of your tasks need from the CPU adds up to less than 69.3% of its total power, rate monotonic provides a mathematical guarantee. No deadline will ever be missed. Ever. It's an incredible promise, but it does mean you're intentionally leaving over 30% of your CPU power unused, just as a safety buffer. All right, On to strategy number 2, earliest deadline first, or EDF. And this one is a whole different ballgame. It's dynamic. Priorities aren't set in stone. Instead, the scheduler is constantly looking at all the tasks that are ready to run and asking just one simple question. Whose deadline is coming up the soonest? Whoever wins that contest gets the CPU. This means a task's priority can literally change from one moment to the next. And you can just see the power of this dynamic approach right here. By constantly reevaluating which task is truly the most urgent, EDF is just smarter. It can handle more complex situations and use the CPU way more efficiently. It packs the tasks together much more tightly, letting us safely use much more of the CPU's power without risking a missed deadline.
So at the end of the day, it's all about trade-offs, right? There's no one perfect answer. RMM is super simple and behaves very predictably when things go wrong. If the system gets overloaded, the low-priority tasks just don't run, but the critical ones are protected. EDF is way more efficient. It can theoretically use 100% of the CPU, but if it gets overloaded, you can get a catastrophic domino effect where every task starts to miss its deadline. Which one you choose depends entirely on what you're building.
But what happens when these neat, tidy mathematical models slam into the messy chaos of the real world? Well, sometimes the beautiful rules of priority can break down in a really terrifying way. It's a problem called priority inversion.
Here's the setup. It's super common. Tasks have to share stuff, right? A sensor, a data connection, a piece of memory. And to keep the data from getting corrupted, a task has to lock that resource while it's using it. So, what happens when your most important high-priority task suddenly needs a resource that some unimportant low-priority task has already locked? Okay, let's play this out because it's a total nightmare scenario. Imagine an ambulance, that's our high-priority task, screaming towards the hospital. It gets stuck behind a slow-moving car, our low-priority task. Annoying, but okay. But then a regular family sedan, our medium-priority task, comes along. It's not as urgent as the ambulance, but it's faster than the slow car, so it just zips past it and keeps going. Now look at the situation. Our ambulance, the most critical task in the system, is now stuck waiting for both the slow car and the regular car. Its priority has been effectively inverted. This is priority inversion. It is a subtle, silent killer of a bug, and it has caused catastrophic failures in real-world systems. The fixes are pretty complex, involving clever tricks where the system can temporarily loan the high priority of the ambulance to the slow car just to get it out of the way faster. It's a really deep, fascinating corner of computer engineering.
So why does any of this matter to you and me? Because these ideas are no longer just for rockets and space shuttles. They are the invisible, absolutely critical foundation of our modern lives.
You know that old saying, Murphy's Law? Anything that can go wrong will go wrong? Well, in real-time systems, that's not a pessimistic joke. It is literally the core design philosophy. You can't just hope you find all the bugs through testing. You have to assume the worst will happen and mathematically prove that your system can handle it. So let's just boil this all down. What are the big things to take away? First, real-time is not about being fast, it's about being predictable. Second, that predictability is created by these ingenious scheduling algorithms like RME and EDF. Third, these aren't just theories. They are the invisible code keeping you safe in your car, in an airplane, or ensuring a medical device works flawlessly. And finally, designing for the absolute worst case isn't being a pessimist. In this world, it's the only way to keep people safe. And that really leaves us with this huge, fascinating question about our future. We are rushing into a world of self-driving cars, robotic surgeons, and AI managing our power grids. These systems are unbelievably more complex than anything we've built before. So how are we going to apply these ironclad principles of predictability to a world run by software that can, by its very nature, be unpredictable? That is one of the single biggest challenges facing the next generation of engineers.